Welcome to this lecture series in linear algebra. In this lecture, we look at the notion of orthogonal complements in the context of inner product spaces, amongst other things. And all we need to follow this lecture are basic definitions about inner product spaces. If there is some interesting property that will be used, I'll perhaps recall it, but let's just be content with this much. Okay, so just give me a second. Yeah, so here are a few problems for practice. And now let us get started. So before we continue, we need a notion that is applicable to general vector spaces. We could have covered this at any time, and I have a feeling that I might have given this as an exercise at some point, but maybe not. So let V be a vector space over any field, not necessarily real or complex. Then a subspace H of V is called a hyperplane if its dimension is 1 less than the dimension of the parent space. So that's the definition, and if you think about it in R3, a hyperplane in R3 is just any two-dimensional subspace, and these are precisely the things that we call planes passing through the origin, but these are the things that we call planes. The notion of a hyperplane just generalizes that. Okay, so here is a very simple lemma about hyperplanes. So if H is a hyperplane in a vector space V and U is a subspace of the vector space V, then the dimension of the intersection of the subspace with the hyperplane is, it doesn't drop by more than 1. So the dimension of U is the dimension of U, but even if you intersect with a hyperplane, the dimension doesn't drop by more than 1. It may remain constant. In case U is contained in H, of course, this would be just the same as the dimension of U. But if that's not the case, then it will drop by 1, not 2 or 3 or more. And the proof is very simple. We know that the dimension of U plus H is the following. Right, and we just shuffle this equation to get right. And now let's say n is dimension of the parent space. Then the right side is what? The right side is dimension U plus n minus 1 by definition of a hyperplane, minus at most n. Since U plus H is after all a subspace of V, this is at most n. So n minus 1 minus, what am I saying? Yeah, n minus 1 minus something that is at most n, and just that observation gives you this. So I hope this is clear. And an immediate corollary of this is the following. If we have a sequence of hyperplanes in a vector space V, then the dimension of the intersection of all of them, has this lower bound. So it's just repeated application of the above one that gives you this. All right. So now we come to the notion of orthogonal complements. So this time we have an inner product space. So V be an inner product space, either real or complex, doesn't matter. Recall that x and y, vectors x and y in V are said to be orthogonal if their inner product vanishes. Right? And the notation for orthogonality is this. So when we write this, we just mean x and y are orthogonal. And note that if x and y are orthogonal, then y and x are also orthogonal. That's that. And here is an observation. So yeah, this is fine. Now here is a definition. So for any subset of the vector space, let's say the subset is named S, we define S perp. So this is read as S perp, or the orthogonal complement of S. So that's something that we are going to define. That doesn't look very nice. So so we are going to define the orthogonal complement of S, and we may also read it as S perp. And what is the definition? The definition is all those vectors in the vector space which are orthogonal to every element in S. So that's the definition of the orthogonal complement of S. Again, S does not need to be a subspace. It is just a subset. Okay. So here is a very simple fact that the orthogonal complement of S is the intersection of the orthogonal complements of all the elements in S. That's just immediate from the definition of S perp. Right here we have a for all, and that is why we have an intersection here. So just make sure you follow this. And now check that this is a subspace of the vector space V. Even though S is not required to be a subspace, this is always a subspace. That's because if you have, let's say, some vector orthogonal, okay, so let's just verify this is a subspace. Right, just for a singleton, let's just verify this is a subspace. And since the orthogonal complement of any subset is just the intersection of orthogonal complement of singletons, it would be intersection of a bunch of subspaces, and hence would itself be a subspace. So just verify this fact for a singleton, and it's clear because if U and V are orthogonal to S, then their sum is also orthogonal to S, and any scale of U or V is also orthogonal to S. So this is a subspace of V, and this is a reverse containment that happens. So if S1 is a subset of S2, which is a subset of V, then the orthogonal complement of S2 is contained in the orthogonal complement of S1. And this is immediate from this equation, because since S2 has more things in it, this intersection runs over more things, and hence this containment is clear. Lastly, one more thing to note. Suppose U is a subspace of the vector space V, and S is a subset of U which spans U. So span of S is U. Then this happens. Then the orthogonal complement of S is same as the orthogonal complement of U. So let me explain this a little bit. So say S is equal to U1 up to UK. Okay, and these vectors, they span the subspace U. So then, simply because S is a subset of U, we have, by the reverse containment fact that we just saw, this containment is already there. So we need to establish the other side. So to do that, we pick something here arbitrarily and show that it is here. So if something is in S perp, we want to show it is here. Okay, but if something is in S perp, let's say V, then V is orthogonal to this, dot dot dot, V is orthogonal to that. Which means V is also orthogonal to every linear combination of these folks. And hence V is orthogonal to everything in U. And hence V is in U perp. So this containment also holds. So I'm not writing that, but I hope it is clear. Alright, let's move on. So here is some pictorial example. So we have the two-dimensional vector space R2, and a subspace of it is given. Let us try to nail down the orthogonal complement of it. So the inner product we will be using is the standard inner product, and let me recall what that is. So it is a map which takes a pair of vectors x and y to that thing, and this is the dot product that we study in high school. So that's that, and therefore just by our experience, high school experience of plane geometry, we can immediately write down what are the things that are orthogonal to everything here. Those things are precisely the things lying on this line perpendicular to this line. So that would be the orthogonal complement. Okay. In R3, again, you have the standard inner product on R3, and there we have this subspace. So its orthogonal complement would be this plane perpendicular to this line. And I hope you can convince yourself of this. This is just a picture, so there's nothing to really argue here, but still. Okay. So now let's also prove a very simple result, that if V is an inner product space, again, doesn't matter if it is real or complex, and we have a non-zero vector, little v in it, then the orthogonal complement of it is a hyperplane. Okay, it should be intuitively clear. For instance, in R2, if you have this vector, then the orthogonal complement is this one-dimensional space, which is a hyperplane. And we also saw this example where we had a one-dimensional subspace. Its orthogonal complement was a plane, which is a hyperplane in R3. So if you take a non-zero vector and take the span of it, it is going to be a one-dimensional space, and hence its orthogonal complement is going to be a hyperplane. So let's prove it in full generality. So define the map phi to the base field. Now the base field could be either real or complex, as right, that's how we define it. So this is a linear map. This is a linear map, and since V is non-zero, this map is not identically zero, because phi of V is V dot V, which is norm of V squared. So this is non-zero, and hence phi is surjective functional. So apply rank nullity. So by rank nullity, kernel phi, dimension of the kernel of phi is dimension V minus dimension F, which is 1. So kernel phi is a hyperplane. But what is kernel phi? Kernel phi is precisely those things which are orthogonal to V, and hence it is this. So that's it. That's the proof. Right? This is kernel phi, and dimension of kernel phi is this, hence kernel phi is a hyperplane. Okay. Now we have this result about orthogonal decomposition. We saw such a result when we were discussing bilinear forms, but let's kind of reprove it, and we will give a slightly different argument. Yeah. So first of all, we note that. Yeah, so what is the statement? I did not speak this statement. The statement is this: V is some inner product space, U is some subspace, then V is the direct sum of U and its orthogonal complement. That's all. So first of all, note that this is trivial. Why is that? The reason is, if we have some vector in this intersection, then V is in U and it is also here, hence it is orthogonal to itself. Everything here is orthogonal to everything here, hence V is orthogonal to itself. So we have, this is 0, which implies V is 0. So you pick arbitrary element in the intersection, you find it is 0, and hence this intersection is at the very least trivial. So now the goal is to show that the sum of the dimensions is the dimension of the parent space. This will finish the proof. Okay, so let K be the dimension of U. Okay, and fix a basis. Okay. Now we have, by our observations earlier, U perp is what? U perp is intersection of the perps of UIs. This is because this is a spanning set. This is a tuple, but you make a set out of it. So this is a spanning set for U. Hence, the orthogonal complement of this set is same as the orthogonal complement of U. But the orthogonal complement of this set is the intersection of all the things, of the orthogonal complements of all the things in the set. And hence, we have this equation. So this implies dimension of U perp is equal to the dimension of the intersection, which, since these are hyperplanes and this is an intersection of k hyperplanes, by the result that we saw about hyperplanes in the beginning of the lecture, we have this is at least dimension v minus k, which is dimension v minus dimension u, and we get this. But since u and u perp, they intersect trivially, the reverse inequality is obvious, and therefore this is actually an equality, and we are done. So that proves our goal, and this proves the orthogonal decomposition theorem. Any vector space can be written as the direct sum of a subspace and its orthogonal complement. Okay. Finally, we will discuss the notion of an orthonormal basis. So again, V be an inner product space, regardless of whether it is real or complex. An orthonormal basis of V is a basis So it's a basis of V such that two things happen. So every vector in the basis has norm 1, and any two distinct vectors in the basis are orthogonal. That's the definition of an orthonormal basis. Before we look at examples, let's see, just let me write down an example here on the side. So if you have Rn, then the standard basis is an orthonormal basis. Okay, and the standard basis in Cn is also orthonormal. So those are examples. And now let us prove this lemma. If this is an orthonormal basis of an inner product space V, then the norm of this linear combination squared is this. And this you can think of as Pythagoras' theorem, or a generalization of it, or a version of it. Maybe not generalization, but a version. So, okay, so how do we prove this? The proof is very simple. Yeah. So the norm of the left side squared is which by properties of inner product is equal to summation right, which is equal to which. So if you fix a j, if you fix a j, the only I which makes this non-zero is j, because vi and vj are orthogonal whenever I is different from j. And if you scale two orthogonal things, you again get two orthogonal things. So this summation is actually this summation, which if you just think about it is this, which is what we have on the right side. So it's very simple. Okay. And lastly, we want to show that every inner product has an orthonormal basis. Every inner product space has an orthonormal basis. So we will do this by induction on n. And I will not spell out all the details, but here is the main core of the proof. So fix an inner product space V. We want to show that this has an orthonormal basis. So let this in V be arbitrary, or rather be non-zero. So if this were a zero-dimensional vector space, we don't care. We don't want to make statements about zero-dimensional vector spaces. So the dimension of V is at least 1. And now you pick a non-zero vector in it and define. So it has some norm. So let's say lambda in the base field be such that this has norm 1. Right? If it did not have norm 1, you can always scale it to make it norm 1. All right. And let us call this thing as u1. So u1 is a unit norm vector in the vector space. Declare or define capital U as span of u1. Right. Now it's possible that capital U is the entire vector space, in which case we are done, because then u1 itself would be an orthonormal basis. But if it is a positive dimensional vector space, so if u equals v, then we are done. If u is strictly contained in v, then u perp is a positive dimensional subspace. So dimension u perp is at least 1. But at the same time, dimension u perp is strictly less than the dimension of v. In fact, it is 1 less than the dimension of v, because the dimension of u is 1. And now just apply induction. So you have a smaller dimensional vector space. By induction, you can find an orthonormal basis of it and just patch u1 to that basis. You will get an orthonormal basis for the entire vector space. So let me write that down. So we can find an orthonormal basis of u perp by induction, call it u2 up to un, and now note that so if you just patch u1 to this guy, you get an orthonormal basis of the entire vector space, because this is, u1 is orthogonal to every other thing. And since this is an orthonormal basis for u perp, everything here has a unit norm, and pairwise inner products are 0. So all the properties you can easily verify, and hence this is an orthonormal basis for the entire vector space V. So that finishes the proof of this. And with that, I also want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.